Hey everybody, today we'll do another video, and today we will do another video, and it's going to be on circuit, AC circuit, right? So this is the problem that we're doing. We actually finding the we finding the impedance of this, right? So you can see that what the problem says. It says determine the equivalent impedance of the circuit shown below, right? So with that being said, let's get started, right? So this is the circuit. I just redraw it. As you can see that we have some inductors, some capacitors, some resistors, and this is the circuit, right? So if this was a paper, you take your pen or your pencil, and then you go like this, right? You find out this is in series, right? These two are in series, and then you come over here, you get a node, and then for that node, you're going down, right? These two also are connected together, right? Those two are connected together, and then you come over here, and then this resistor, that inductor, and that capacitor are connected together, which means that they are in series, right? And these two technically are also connected in the same you would say in the same branch, right? Or node, because this is the branch, right? This is the node, but then the branch is down here. So that would be, in series. And then this with this two with all of this is connected in parallel. So this is in series, and this with this, the whole thing is in parallel. Will be like a series parallel circuit, right? And then of course this is in series, so that will make a series parallel circuit. Okay, so with that being said, let's get started. So let's see, and this is the answer, right? So that's the answer right there, A, and we will see how we get that A, right? Because the answer has been rounded off, right? And that's why I wanted this, I decided to put the picture over there, because that way, people can see it, right? And the answer is not what we get, right? So the answer has been rounded off a little bit, right? So I don't want, if somebody try this problem and they will get a different answer, and they will say, well, my answer is different. Well, it's a little bit different because, it's been rounded off, right? Okay, so let's get started, right? So with that being said, remember from basic AC circuit, if a circuit is like this, right? I don't know if you guys remember, but let's say that you have a circuit like this, another circuit, another resistor like that. Right. So notice that this and this will be R2, this will be R3, this will be R1. So technically R1 would be in series, and R2 and R3 are in parallel. So the combination of the circuit would be R1 plus R2 times R times R3 over R1 plus R3. Actually, this should be R2, right? So because, and the reason why is like that is because, remember, this, right? These are in parallel, right? These are in parallel, and this is in series. So the combination of that will be R equivalent will be that, right? So I hope that makes sense a little bit. So that will be R equivalent, right? So that would be the that will be the situation, right? So it's going to be similar here, right? So just want to put that there so to refresh the memory a little bit. Okay, so remember, we now we're dealing with resistors and a combination of inductors and capacitors, right? So which means that we have a J, right? And instead of having a pure resistance, we have a J, and we have a J, right? Which is imaginary numbers, imaginary values of the impedance, right? So impedance is basically when you have this type of in other words, it's AC circuits when we use capacitors and inductors, right? So basically, we will try to do this kind of quick, right? So let's get started, right? So okay, so let me just move this up a little bit. All right, so let's do this. You know that this and this are in series, right? This and this is in series, and this and this and this is in series. So I can actually, like a regular mathematics, you can add anything that has like terms. In this case, I have J and J, right? I got a negative 10J and I have a 5J, so therefore I can add those together and then make it one, right? One element, and the whole thing. This will be combined to one element. And of course, the greater number is 10J, so the capacitor will have the priority. So the capacitor will be the one showing up in the circuit, right? So we want to get rid of that inductor, right? So I will draw the circuit, I will redraw the circuit, and I will do, right? And then I will do a branch for that, and another 10 ohms, right? And then I will have right. So now I can actually do this capacitor can actually so let me just erase this because this is not so right. So right, so we have this. This is okay. So it's kind of weird. Okay, so you can see right there, right? Much better. Okay, so now we have this, right? So we have the value of this is negative 5J ohms, right? Because we added them together, and this is 2, right? I believe that is 2. Yep, that's 2 ohms. 2 ohms, right? So the value of this is negative 5J ohms. And of course, this is 2 J ohms, and this is 10 ohms, right? So now that we have this, right, we can use the little series and parallel circuits, right, formula, so we can actually do this and this, right? Notice that this is in parallel, this and this are in parallel, so this two, this and this are in parallel, right? So what we can do the following. So we can say that 10, but remember, I cannot add this, right? I cannot add this and this because they're not like terms. I cannot add like this because they're not like terms. So therefore, I have to do the math accordingly. Whatever corresponds to this two, and whatever corresponds to this two, right? So it's going to be 10 minus 5J, right, times 2 minus 5J, right, over 10 minus 5J plus 2 minus 5J, like that, right? Now all I have to do at this point is just do the math, right? And at the same time, be careful because it's going to be some imaginary numbers popping up. Okay, so let's do it. So it's going to be if I multiply this and this is going to be 10, and this is this, and this is going to be negative 50, correct? So it's going to be 20, right? And then this time this is going to be negative 50. I don't know why I say 10, but right, so it's negative 50J, right? And then this, and so I did the other. Now that I gotta do the inner or this and this. So it's going to be what? It's going to be negative 10J minus, actually it's going to be a plus now, plus 25J squared 25. Okay, so in the bottom I am adding those two, which is going to be 12 minus 10, right? Minus 10J. So with that being said, as you know that, so remember from imaginary numbers that I squared is equal to, in imaginary numbers, is equal to a -1, right? Okay, so if that is the case, what we can do right here, do some simplification on the top, and I get 20, and then we do 60, right? J minus, plus, and then we do a -1 for J, right? J represent I, so it's 25, right? And then 25 being multiplied by that -1, and that is going to be over 12 minus 10J, which is going to simplify to this one. -25 plus 20 is going to be a -5 minus minus 60J, right? And of course, that's going to be over 20 minus 10j, right? So with that being said, now we have a small value, right? But remember this, we have to get rid of we have to have like in a form of a rectangular form that doesn't include this, fraction. So to do that, we multiply by the conjugate. We multiply by the conjugate. Right. So we multiply by conjugate. So, and remember, we have to add those ones in series from the circuit. So we have to add those. So we multiply by the conjugate. And what is the conjugate in this case? So the conjugate means that I will multiply by whatever opposite sign is in the bottom, right? Top and bottom multiply by the opposite. So in this case, it's going to be negative 5 minus 60 j, right? And then multiply top and bottom by whatever. See, this is a negative, so I need to change that to a positive. So I gotta do 12 plus 10j on the top, and I gotta do on the bottom. I gotta do 12 minus 10j times, now it's times, right? Times 12 minus, plus 10j. When we do that, we multiply 5 times, negative 5 times 12 is negative 60. And then this times this is negative 50j. And then we do the inner, which is going to be 720, right? J, right? This times this, and then this times this is going to be negative 600 j squared. And on the bottom, we do this times this is 124, right? 12 times 12, 124. I'm sorry, 144. 144. All right, so 12 times 12 is 144. 144. And this times this is going to be negative plus 120. Plus 120j. And the inner is going to be negative 120j. And the outer is going to be negative 100j squared. And see, now you can see that the whole purpose of doing this is to get rid of this. See, now I got this. This is gone, right? So, right. So we can simplify something on the top too. On the top, I can actually combine this and this, right? So I can say that negative 60 minus 770j minus 600j squared all over 144 minus 100j squared. All right, so now we're seeing that we're getting there, right? So now what I need to do is substitute -1 for this, right? J squared, and I get what? I get I get 60 minus 70, 770J, 770J minus, right, 600 times a negative 1, right, all over 144 minus 100 times a negative 1, right, which on the top is going to be equal to, this is going to be equal to plus 600, and minus 60 is going to be, it's going to be 540 minus 770J over 244, right? Now, you can see that we have a pure number in the bottom, and that's what we want, right? So in this case, what we want to do is we want to simplify that, right? So we do that. We can say that the combination of the parallel of this parallel, which is going to be 10, right? 10 minus 5J in parallel with 2 minus 5J is equivalent, that is equal to, right? That is equivalent to 2.21 ohms minus 3 minus 3.15 J ohms, right? You divide this into that, and you divide that into that, and you get that, right? Okay. So now that we have it this, right, we can actually make it a series circuit. See that? Because the parallels are done. We're done with the parallel element, right? So we can actually do, right? Right. So now we can do another resistor. And then notice that this is a negative 3.15J. That is a capacitor. Right? And then we can just, oops, I'm going to the wrong direction with this. This is, okay, so let me just, all right, so this is the C you're trying to find, right? So now let's put back the values. So here is 10, right? 10 ohms, I believe, from the figure, from the book. Yeah. And this is 2 J, J2, right? So all right, and then here is 2.21 ohms, and here we have, what? We have negative 3.15 J, right? And now Now, all we have to do right now is add these values, right? Add these values, this resistor, and this capacitor, and this inductor, right? So when I add that, I get the Z equal to 12 point, actually 12 ohms even. Okay, so this is what I'm trying to make, right? So equivalent to what? So it's very close, right? So it's very close to, well, the answer should be like this, right? So it should be 12, 21.21 ohms, right? And then minus, and then when I add this, and this is going to be negative 1.15 J, right? But also that is equivalent to what? It's going to be equivalent to 12 ohms minus 12 ohm minus J, right? Minus 1J, right? Because yeah, that's smaller, and this is also smaller, which, and that's why I wanted, to make that point that. So. All right, so that is the answer, guys. That is the answer for this problem. I hope you learned something in this video, and we learn something every day over here at the Conservative Engineering Academy, because Jesus is awesome with us, right? That's it. We at the Conservative Engineering Academy, we are not afraid to mention Jesus, right? So Jesus is good, and therefore we learn something every day, right? Thank you, Jesus, and thank everybody. Bye-bye.